Module 22, Lecture A, Centroid Clustering. By the end of this lecture, you will be able to apply k-means and mini-batch k-means to unlabeled data, use inertia and silhouette analysis to compare cluster counts, and fit affinity propagation and mean shift with key parameter controls. K-means basics. K-means comparison. K-means is a clustering method for finding groups in unlabeled data. After choosing the number of clusters, the algorithm assigns each data point to the nearest centroid, then updates each centroid to the average position of its assigned points. This repeats until the groupings change very little, making it useful for tasks like customer segmentation or analyzing student engagement. K-means is different from classification because it groups data by similarity without using labels. This makes it useful for exploring data and finding natural patterns before deeper modeling. Choosing the right number of clusters is important because too few can hide real differences, while too many can create misleading subgroups. K-means and mini-batch k-means use the same basic clustering idea, but differ in how they update clusters. Standard k-means uses the full dataset each time, giving more stable results on smaller data. Mini-batch k-means uses small random samples, making it faster and more practical for large datasets, though sometimes slightly less accurate. The best choice depends on the balance you need between accuracy, clarity, and efficiency. Minimizing cluster variance. K-means clustering groups data by assigning each observation to the nearest centroid, which represents the average position of a cluster. The centroids are then adjusted so the clusters become more compact and similar within each group. Its main goal is to reduce the spread of points around their centroids, such as grouping retail customers with similar spending and visit patterns. Cluster variance shows how far points in a cluster are from its centroid. Low variance means the cluster is compact and consistent, while high variance may mean the group is too broad or too few clusters were used. K-means tries to minimize this variance by forming compact, roughly spherical groups, making the results easier to interpret and use for decisions. K-means works best when clusters are clearly separated and features are properly scaled, because it aims to reduce variation within each group. But low variance does not guarantee that the clusters match real-world categories. In fields like healthcare, compact patient groups still need expert interpretation to determine whether they are meaningful and useful for the problem. K-means fitting. Fitting K-means means grouping unlabeled data into a chosen number of clusters based on similarity. The algorithm starts with temporary cluster centers, assigns each point to the nearest center, then moves each center to the average of its assigned points. This repeats until the centers stop changing much or another stopping rule is reached, producing compact groups such as customer segments based on spending and preferences. K-means clustering is sensitive to the initial placement of centroids, so poor starting points can lead to weaker clusters. To improve results, modern methods use smarter initialization and often run the algorithm several times, keeping the solution where points are most tightly grouped around their centroids. This matters in real datasets with overlap or outliers, where careful setup and feature preparation can produce more reliable clusters. Before using k-means, scale your data so distance comparisons are meaningful and no feature dominates the clustering. After the model is fitted, each point receives a cluster label, and each cluster has a centroid that represents its typical profile. These labels are not right or wrong. They summarize patterns and make large datasets easier to interpret. Python code. K-means fitting. This example applies k-means clustering to unlabeled data points. Scaling the data helps make distance comparisons fair, and the result identifies cluster labels along with their centroids. We import key Python tools for a k-means clustering workflow. NumPy supports numerical computation. Matplotlib helps create visualizations. And Scikit-Learn provides machine learning tools. From Scikit-Learn, we use k-means clustering to group data, a blob dataset generator to create synthetic clustered data, and a standard scaler to normalize features so they contribute evenly to distance calculations. We create a small unlabeled dataset using Scikit-Learn's makeBlobs function, which generates points that form 3 natural groups. The dataset contains 180 samples, with a moderate spread around each group center. A fixed random state is used, so the same data is produced every time the code runs. Before fitting the k-means model, the code verifies that the dataset has 180 rows and 2 features. If the data does not match this expected structure, it raises an error instead of continuing. This check helps prevent problems during clustering by ensuring the input is in the right format. We use a standard scaler to normalize the dataset, so each feature has a comparable influence on clustering. Applying the scaler computes each feature's mean and standard deviation, and then transforms the data to have a mean of 0 and a standard deviation of 1. This is important for distance-based methods like k-means, where unscaled features can distort the results. A k-means model is set up to find 3 clusters in the scaled data. It runs with 10 different starting centroid choices to improve the result, and a fixed random seed makes the output reproducible. The model then assigns each data point to the nearest centroid, producing a cluster label for every point. After k-means finds centroids on scaled data, we convert those centroids back to the original feature scale using the scaler's inverse transform method. This makes the centroid values easier to interpret and compare with the original dataset. The output summarizes key k-means clustering information: the Scikit-Learn version for reproducibility, the chosen number of clusters, the inertia score showing how tightly points fit their clusters, and the first 10 assigned labels as a quick preview of the results. Create a plotting area with Matplotlib. Then display the dataset as a scatter plot, using the first 2 feature columns as the horizontal and vertical coordinates. Color each point by its cluster label with the Viridis color map, and use a moderate point size so the clusters are easy to see. Use Matplotlib's scatter method to plot the centroids by taking their x and y coordinates from the centroid array. Make them easy to identify by coloring them red using a large X-shaped marker and adding a centroids label for the legend. The plot is made easier to understand by adding a clear title about k-means fitting on unlabeled data, labeling the 2 axes as Feature 1 and Feature 2, and including a legend. Together, these elements help viewers interpret the data and distinguish key plot components, such as the centroids. The final step is to display the plot using Matplotlib's show function. This renders the k-means clustering results on screen, including the data clusters and their centroids, so the outcome can be viewed visually. This script creates a synthetic dataset with 3 clear groups, scales the features, and fits a k-means clustering model with 3 clusters. The model is run with multiple initializations to improve the final fit, then reports key results such as the Scikit-Learn version, inertia, and sample cluster labels. Finally, it visualizes the clustered points and marks the centroids, showing how well k-means captures the dataset's natural structure. K-means evaluation. K-means initialization. K-means clustering depends heavily on the initial placement of its centroids. The algorithm repeatedly assigns points to the nearest centroid, and moves each centroid toward the center of its assigned points. But it may settle on a locally optimal grouping rather than the best overall one. In practice, poor starting positions can split natural groups or merge distinct ones, making the final clusters mathematically valid, but less useful for decisions. Centroid initialization in k-means can strongly affect how cluster counts look under metrics like inertia and silhouette scores. Poor starting centroids can make clusters appear less compact or less well separated than they really are, leading to misleading evaluations. As a result, a bad initialization may make the chosen number of clusters seem wrong when the real issue is the starting setup. K-means usually works better when initial centroids are placed deliberately and spread across the data instead of chosen randomly. This can produce more stable clusters, especially when groups are close together or differ in size. Still, metrics such as inertia and silhouette scores must be interpreted carefully, because low inertia can simply reflect using more clusters, and silhouette results should be checked against domain knowledge. Good initialization helps these metrics better reflect the real structure in the data. Python code, k-means initialization. Compare different k-means initialization choices on generated clusters, because the starting points can affect inertia and silhouette scores. Using better initializations makes it easier to judge the right number of clusters reliably. We import the main tools needed for k-means clustering: NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for machine learning. From Scikit-Learn, we use k-means to form clusters, a blob data generator to create sample data, and the silhouette score to evaluate cluster quality. We generate a synthetic clustering dataset using Scikit-Learn's makeBlobs function. It creates 450 data points arranged around 3 centers, with a standard deviation of 1.25 to control how spread out the clusters are. A random state of 42 makes the results reproducible. The function returns both the data points and their true group labels. But for clustering, we mainly use the data points themselves. Before fitting the model, the code verifies that the dataset has 450 rows and 2 features. If it does not, it raises an error to signal the wrong format. This check helps ensure the data is ready for clustering and prevents later analysis problems. We create a k-means model to group the data into 3 clusters. The cluster centers are initialized randomly, and the model runs only once with that initialization. A fixed random state of 42 makes the results reproducible each time the code is run. The k-means model is initialized randomly, then used to fit the data and assign each point to one of 3 clusters. The silhouette score is then calculated to evaluate how well the points fit within their assigned clusters compared with other clusters. A higher silhouette score means the clusters are more clearly separated. This setup creates a k-means clustering model to find 3 clusters using the k-means ++ initialization method. This method chooses starting centroids more strategically by spreading them across the data, which can improve clustering results. The model runs once with this initialization, and a fixed random state of 42 makes the results reproducible. The code applies k-means clustering using k-means ++ initialization, which helps choose better starting points. After fitting the model, each data point is assigned a cluster label. It then uses the silhouette score to evaluate clustering quality, where a higher score means the clusters are more clearly separated. The output reports the Scikit-Learn version for reproducibility, then compares 2 k-means initialization methods. For both random initialization and k-means ++, it shows inertia, where lower values mean tighter clusters, and the silhouette score, where higher values mean better separation. These metrics help judge which initialization gives better clustering results. A plot is prepared with a 7 by 5 inch figure. Then the data points are shown using a scatter plot. The first two feature columns provide the horizontal and vertical positions, while the cluster labels from k-means++ set each point's color. A various color map and moderately sized markers make the clusters easier to distinguish. The plot uses Matplotlib's scatter method to show the final cluster centroids. It takes the centroid X and Y positions from the model's cluster centers, then displays them as large, red X markers. These points are labeled as final centroids so they can be identified clearly in the legend. The plot presents the result of k-means++ initialization with 3 clusters. The axes are labeled Feature 1 and Feature 2 to show the data dimensions, and a legend identifies key elements such as the cluster centroids. The visualization is then displayed so the clustering result can be assessed visually. This script compares random initialization with k-means++ for k-means clustering on a dataset with 3 natural groups. It fits both models, then evaluates them using inertia for cluster compactness and silhouette score for separation. K-means++ usually performs better with lower inertia and higher silhouette scores. The script also visualizes the k-means++ result by coloring points by cluster and marking the final centroids. Multiple initializations. K-means clustering is sensitive to where its centroids start, so a single run can produce misleading clusters. Poor initial positions may cause the algorithm to settle on a suboptimal grouping that does not match the data's real structure. Because different starts can lead to different inertia values and cluster patterns, it is risky to rely on one run, especially with complex or noisy data. Running k-means several times with different starting points makes the clustering results more reliable by choosing the run with the lowest inertia. It does not guarantee the best possible solution, but it reduces the chance of being misled by a poor random start. When comparing different numbers of clusters, each option should be tested multiple times, so the elbow method reflects more stable inertia values. When running k-means with multiple starting points, evaluate clusters using both inertia and silhouette analysis. Inertia shows how tightly points group within clusters, while silhouette scores show how well points fit their assigned cluster compared with others. Because poor initializations can create loose or overlapping clusters, repeating the algorithm helps produce more reliable results. Still, the best numerical score should be judged in the context of the real decision being made. Python code. Multiple initializations. This example compares different ways to initialize k-means. Using repeated starts gives more reliable inertia comparisons than a single start, helping show how initialization affects clustering results. We import the main tools needed for k-means clustering: NumPy for numerical work, Matplotlib for visualization, and Scikit-Learn for machine learning. From Scikit-Learn, we use k-means clustering, synthetic data generation, and the silhouette score to create datasets and evaluate clustering quality under different initialization strategies. We generate synthetic clustering data with Scikit-Learn's make_blobs function. The dataset contains 450 samples, grouped around 4 centers, with a cluster spread controlled by a standard deviation of 1.25. A random state of 42 makes the results reproducible, so the same data is created each time for consistent testing and comparison. This code checks that the clustering data has the expected structure before analysis begins. It verifies that the feature data contains 450 rows and 2 columns, and raises an error if the shape is different. This helps keep the example clear and prevents later steps from using incorrectly structured data. We prepare to compare k-means clustering results by testing cluster counts from 2 to 6. Empty storage is set up for inertia from single and multiple starts, along with silhouette scores from multiple starts. Inertia shows how compact the clusters are, while the silhouette score shows how well the clusters are separated. For each chosen number of clusters, a k-means model is created with one random initialization and a fixed random state for reproducibility. The model is then fit to the feature data and used to assign each data point to one of the clusters. A k-means model is created with a chosen number of clusters and run with 20 different starting points to make the results more reliable. A fixed random state keeps the process reproducible. The model is then fitted to the feature data and used to assign each data point to a cluster, producing a more stable clustering solution. The process records inertia for both single start and multiple start k-means models to compare how tightly their clusters are formed. Multiple initializations can improve the result by reducing the risk of settling in a local minimum. It also records the silhouette score for the multiple start model, which measures how clearly separated the clusters are. The code reports the Scikit-Learn version to support reproducibility, then uses silhouette scores from repeated start k-means to choose the best number of clusters. It prints this optimal cluster count and compares inertia for 4 clusters, using single versus repeated starts. Since lower inertia means tighter clusters, the comparison highlights how multiple initializations can improve k-means results. This plot compares k-means inertia across different numbers of clusters for 2 initialization settings. It shows one line for a single initialization run and another for 20 initialization runs, with inertia on the vertical axis and the number of clusters on the horizontal axis. The title, labels, legend, and grid make it clear that lower inertia is better and help compare how initialization count affects the results. This script shows how initialization affects k-means clustering on synthetic data with 4 clusters. It compares single and multiple initializations across different cluster counts using inertia and silhouette scores. Multiple initializations usually produce lower inertia and a more stable elbow curve, while silhouette scores help identify the best number of clusters. Overall, the example highlights that repeated starts make k-means results more reliable. Mini-batch k-means. Mini-batch k-means is a faster version of k-means designed for large datasets. It updates cluster centers using small random samples instead of the full dataset, which reduces computation and makes it easier to test different numbers of clusters. It is useful for large-scale data such as customer sessions or vehicle traces, and the results can still be evaluated with measures like inertia and silhouette analysis. When evaluating mini-batch k-means, use inertia to judge how tightly points cluster around their centroids. Adding more clusters usually lowers inertia, but the goal is to find where the improvement starts to level off. Mini-batch k-means makes this comparison faster, even if its inertia values differ slightly from full k-means. Focus on the overall pattern and look for a clear bend in the curve, especially when it fits the real-world context of the data. Silhouette analysis helps evaluate whether mini-batch k-means clusters are compact and well separated. Higher scores suggest points fit their own clusters better than nearby alternatives, making the score useful when choosing the number of clusters. Because mini-batch k-means relies on random samples, results should be checked across repeated runs and interpreted with domain knowledge. Its main value is enabling fast, scalable comparison of clustering options. Python code mini-batch k-means. Compare mini-batch k-means results across different cluster counts using inertia and silhouette scores. These measures may point to different choices, but together, they help identify a reasonable candidate for the number of clusters. This setup imports the main tools needed for a clustering example. It uses NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn tools to generate synthetic clustered data, scale the features, run memory-efficient mini-batch k-means clustering, and evaluate the result with a silhouette score. The Scikit-Learn version is also imported to help check compatibility. We generate synthetic data with the makeblobs function to create 900 samples grouped into 4 clear clusters. A standard deviation of 1.25 controls how spread out the points are, and a random state of 42 makes the dataset reproducible. This structured dataset is useful for testing clustering methods such as mini-batch k-means. We use a standard scaler, so each feature contributes equally to distance calculations. It adjusts the data by removing each column's mean and scaling it to unit variance. Applying the scalar's fit and transform method learns the needed values from the data and produces features with a mean of 0 and a standard deviation of 1. Before clustering, the code verifies that the scaled data has 900 rows and 2 columns. If the dimensions are different, it raises an error to signal the mismatch. This check helps ensure the clustering algorithm receives data in the expected format. We test mini-batch k-means using cluster counts from 2 to 7. For each model, we store its inertia and silhouette score so we can compare how well different numbers of clusters perform. For each chosen number of clusters, a mini-batch k-means model is created using that cluster count. The model updates cluster centers with batches of 64 samples, runs 10 different initializations to select the best result, and uses a fixed random state of 42 so the results can be reproduced. The model clusters the scaled data for each tested number of clusters, assigning every point to a group. It then records inertia to measure how compact the clusters are, and the silhouette score to measure how well the clusters are separated. Together, these values help judge the quality of the clustering. To choose the best cluster count, find which silhouette score is highest using NumPy's argmax function. Then use that position to select the matching cluster count from the predefined options. This gives the number of clusters with the strongest separation according to the silhouette score. The code reports the Scikit-Learn version, then selects the best number of clusters using the highest silhouette score, which indicates better cluster separation. It also notes that inertia decreases as the number of clusters grows, but with diminishing returns. Together, these results help choose a balanced value for k by considering both separation and compactness. The inertia and silhouette values are first converted into numerical arrays so they can be processed efficiently. Each set is then scaled by dividing its values by the largest value in that set. This normalization puts both metrics on a comparable scale, making them easier to compare in the final plot. This plot compares mini-batch k-means performance across different numbers of clusters. It shows scaled inertia and scaled silhouette scores on the same chart, using separate marked lines and a legend to distinguish them. The axes label the cluster count and the scaled metric values, making it easier to visually judge which number of clusters gives the best balance between the two metrics. This script uses mini-batch k-means to cluster synthetic data with 4 true centers. After scaling the features, it compares cluster counts from 2 to 7 using inertia and silhouette scores. Inertia improves as more clusters are added, but the silhouette score gives a better balance of compact and well-separated groups, pointing to 4 clusters as the best choice. The final plot compares these scores to support that decision. Mode clustering. Silhouette scores. Silhouette scores help evaluate clustering by showing whether points are close to others in their own cluster and well separated from other clusters. They are especially useful for methods like affinity propagation and mean shift. where the number of clusters emerges from parameter choices rather than being set directly. A high score suggests clear, meaningful groups, while a low score points to overlap or poor assignments. Silhouette scores help judge how affinity propagation settings affect the number and quality of clusters. A loose preference can create too many small clusters, while a restrictive one can merge distinct groups. Silhouette analysis shows whether clusters are compact and well separated, helping choose settings that produce meaningful, interpretable structure. In mean-shift clustering, silhouette scores can help choose a bandwidth by showing how well the resulting clusters are separated. A small bandwidth may create too many clusters by reacting to minor variations, while a large bandwidth may merge distinct regions. For example, rideshare pickup data could be split into nearby corners or combined across very different areas depending on the bandwidth. Silhouette scores are useful, but they should be considered alongside domain knowledge and visual inspection. Python code. Silhouette scores. Use silhouette scores to compare clustering settings. For methods like affinity propagation and mean shift, which determine the number of clusters indirectly, higher silhouette scores indicate clearer separation between clusters. We import the main tools needed for a clustering workflow: NumPy for numerical arrays, Matplotlib for visualization, and Scikit-Learn components for data generation, pre-processing, clustering, and evaluation. The workflow uses synthetic blob data, standardizes the features, applies affinity propagation and mean shift clustering, and measures clustering quality with the silhouette score. The Scikit-Learn version is also imported to document the library environment. We create a synthetic dataset with Scikit-Learn's makeBlobs function to test clustering methods. The dataset contains 300 points arranged around 4 natural centers, with a moderate spread controlled by the cluster standard deviation. A fixed random state makes the same dataset reproducible each time the code runs. We standardize the dataset with Scikit-Learn's standard scaler, so all features are on a comparable scale. This is especially important for distance-based clustering, where larger scale features could otherwise dominate the results. The scaler is fit to the data, and then transforms the features, so each has a mean of 0 and a standard deviation of 1. Before clustering, the code verifies that the scaled data has 300 rows and 2 columns. If the shape is different, it raises an error to signal that the data is not in the expected format. This check helps prevent problems when fitting the clustering models. The code first reports the Scikit-Learn version to help confirm compatibility. It then prints a header explaining the upcoming results, including the clustering method and settings, the number of clusters found, and the silhouette score, which indicates how well the clusters are separated. The setup prepares a small experiment to compare clustering results under different parameter choices. It stores the outcomes and tests 2 methods: affinity propagation with 2 preference values, and mean shift with 2 bandwidth values. This makes it possible to see how each parameter setting changes the clustering behavior. The process loops through each parameter setting and builds the appropriate clustering model. If the method is affinity propagation, it uses the given preference value, a damping factor of 0.9, and a fixed random state for reproducibility. Otherwise, it creates a mean shift model with the specified bandwidth and bin seeding enabled for faster processing. Each model is also given a label based on its key parameter. The fit-predict method trains the clustering model on the standardized features and assigns a cluster label to each data point. Then, NumPy's unique function is used to count the distinct labels, which gives the total number of clusters found in the dataset. The code only evaluates clustering when the number of clusters is meaningful, more than 1, but fewer than the number of data points. In that case, it computes the silhouette score using the standardized features and cluster labels, where a higher score means the clusters are better separated. If the clustering is not valid for evaluation, it assigns a not a number value instead. The code saves each clustering result by recording the method, setting, number of clusters, silhouette score, and assigned labels. This makes it easy to compare different configurations later. It also prints a short performance summary for each run, including the cluster count and silhouette score rounded to 3 decimal places. The process keeps only clustering results with valid silhouette scores, then selects the result with the highest score as the best configuration. It then separates that result into its key details, including the clustering method, settings, number of clusters, score, and assigned labels, so the optimal setup can be referenced easily. The code reports the clustering method that achieved the highest silhouette score. It shows the winning method, its settings, and the score rounded to 3 decimal places, giving a concise summary of the best performing clustering configuration. We create a plot canvas with a 6 by 4 inch figure, then draw a scatter plot using the first 2 scaled feature columns as the coordinates. Each point is colored by its assigned cluster label and sized for visibility. This gives a quick visual check of how well the clustering separates the data. The code adds a clear title and axis labels to explain that the plot shows the best clustering mode based on silhouette score, using 2 standardized features. It then displays the plot so the clustering results can be visually checked. This script compares affinity propagation and mean shift on a standardized synthetic dataset with 4 clusters. It tests different settings, counts the clusters each method finds, and uses silhouette scores to judge how well separated they are. It then reports the best performing method and settings, and visualizes that clustering with a scatter plot. Affinity propagation. Affinity propagation is a clustering method that chooses representative examples directly from the data, so the number of clusters does not need to be set in advance. It treats every data point as a possible cluster center, and uses repeated message passing to decide which points best represent others. The result is a set of exemplars with nearby points assigned to them, making it useful for grouping data such as customer profiles, documents, or images around real patterns. In affinity propagation, the preference setting controls how many exemplars, and therefore clusters, the algorithm selects. Higher preference creates more detailed clusters, while lower preference produces broader groupings. Damping helps smooth the message passing, so the algorithm can converge more reliably. Both settings should be tuned, using validation measures such as silhouette scores. Affinity propagation depends on similarity, so data representation and feature scaling are important to avoid distorted clusters. It can be computationally expensive on large datasets, making it better suited to smaller datasets or carefully selected samples. Its main advantage is interpretability, because each cluster is represented by a real example, which helps explain results in areas such as medicine or education. Python code. Affinity propagation. This example uses affinity propagation to cluster unlabeled points by selecting real observations as cluster centers, called exemplars. The preference setting controls how many clusters the method discovers. We import the main tools needed for a clustering workflow: NumPy for numerical arrays, Matplotlib for plotting, and Scikit-Learn for machine learning. From Scikit-Learn, we use affinity propagation to find cluster exemplars, a synthetic data generator to create clustered test data, the silhouette score to evaluate cluster quality, and the standard scaler to make features comparable for distance-based clustering. We create a synthetic clustering dataset using Scikit-Learn's makeBlobs function. It generates 180 data points arranged around 4 cluster centers, with a standard deviation of 0.75 to control how spread out the groups are. A random state of 42 makes the dataset reproducible each time the code runs. Before clustering, the features are standardized, so no single axis dominates the similarity measure. A standard scaler removes the mean and scales each feature to unit variance. Applying its fit and transform process computes the scaling values and produces features ready for clustering. Before fitting the clustering model, the code confirms that the scaled data has the expected structure: 180 rows and 2 numeric features. If the shape is different, it raises an error to stop the process. This check helps prevent model fitting problems caused by incorrectly formatted data. We configure an affinity propagation clustering model by setting the preference to -35, which affects how many cluster centers the algorithm finds. A higher preference generally leads to more exemplars. The model also uses a damping factor of 0.85 to support convergence, and a random state of 42 for reproducible results. Affinity propagation is applied to the scaled features to assign each data point to a cluster with an exemplar as its center. The model then provides the indices of these exemplars, which identify the actual data points chosen as cluster centers. Counting those exemplar indices gives the total number of clusters found. The code only calculates a silhouette score when more than one cluster is found, because the score is meaningful only for comparing at least 2 clusters. If there are multiple clusters, it measures how well separated they are, using the scaled features and cluster labels. If there is only one cluster, the score is set to 0, because it does not apply. The output reports key details for evaluating the clustering run. It shows the Scikit-Learn version for reproducibility, the preference value that affects how many exemplars and clusters are chosen, the number of clusters found, and the silhouette score, which indicates how well the clusters are separated. Create a plotting canvas with a 7 by 5 inch figure. Then make a scatter plot using the first 2 scaled feature columns as the x and y coordinates. Color each point by its cluster label with the tab 10 colmarp, so the clusters are easy to distinguish, and use a point size of 35 for clear visibility. The scatter method in Matplotlib is used to highlight the exemplar points selected by the affinity propagation model as cluster centers. These points are taken from the scaled feature data using their exemplar indices, then plotted in black with a large X-shaped marker so they stand out. A legend label identifies them as exemplars in the visualization. The plot visualizes affinity propagation clustering by showing the clusters and their selected exemplars. Its axes represent the 2 scaled features being compared, and a legend helps distinguish key elements such as the exemplars. The visualization is then displayed for viewing using Matplotlib. This script applies affinity propagation clustering to a scaled synthetic dataset with 4 underlying centers. A preference value of -35 helps control how many exemplar points are chosen as cluster centers. After fitting the model, the script reports the Scikit-Learn version, the number of clusters found, and the silhouette score when it is valid to compute. It also visualizes the assigned clusters and marks the exemplar points with black crosses. Mean shift. Mean shift is a clustering method that finds dense regions in data without requiring a preset number of clusters. It repeatedly moves a window toward the average position of nearby points until groups converge around density peaks. This makes it useful when cluster counts are unknown or when clusters have irregular shapes. In mean shift clustering, bandwidth controls the neighborhood used to estimate local density, so it strongly affects the clusters found. A small bandwidth detects finer detail and can create many small clusters, while a large bandwidth blends nearby groups into broader clusters. The best choice depends on the feature scale, the desired level of detail, and the goals of the analysis. Mean shift works best when data is properly scaled, so no feature dominates because of its units. It can be computationally expensive on large datasets, and a single bandwidth may struggle when cluster densities vary. Even so, it is useful for finding dense patterns without choosing the number of clusters in advance, such as taxi hotspots or natural groupings in sensor data. Python code, mean shift. Mean shift clustering groups unlabeled points by finding dense regions in the data. The bandwidth setting controls how many dense centers, or modes, are discovered, which determines the resulting clusters. We import key Python libraries for a mean shift clustering example. NumPy supports efficient numerical work, and Matplotlib helps visualize the results. From Scikit-Learn, we use mean shift to find clusters without choosing the number in advance, a blob data generator to create test data, and a standard scaler to put features on the same scale before clustering. We generate synthetic clustered data using Scikit-Learn's makeBlobs function. The dataset contains 240 points arranged around 3 cluster centers, with each cluster given a different spread. A fixed random state of 42 makes the generated data reproducible each time the code runs. Before clustering, we standardize the data so each feature has a mean of 0 and a standard deviation of 1. This makes distances between points more comparable and prevents features with larger ranges from dominating the clustering results. A mean shift clustering model is created with a bandwidth of 1.0, which sets the neighborhood size for finding dense areas in the data. Bin seeding is used to make the process faster by starting from grid-based cluster centers. The model is then applied to the scaled data, assigning labels that group nearby points around dense regions. After mean shift finds the cluster centers, those centers are still in the scaled feature space used for clustering. To interpret them in the original data context, we apply the scalar's inverse transformation. This converts the centers back to the original feature scale, making their positions meaningful relative to the initial data. Before analyzing clustering results, verify that the number of cluster labels matches the number of data points. This confirms that every point was assigned to one cluster. If the counts differ, an error should be raised because the clustering process did not handle the data correctly. The clustering results are summarized by counting the unique cluster labels, which gives the number of groups found by the mean shift algorithm. The output also reports the Scikit-Learn version for reproducibility, the model's bandwidth value, and the final number of discovered clusters. A new plotting area is created with Matplotlib, sized 7 by 5 inches. The data points are then shown in a scatter plot using the first 2 columns as coordinates. Each point is colored by its cluster label with the Viridis color map, with moderate size and slight transparency to make overlapping points easier to distinguish. We use Matplotlib's scatter function to highlight the cluster centers found by the mean shift algorithm. These centers represent dense regions in the data, and they are shown as large red X markers, so they stand out from the other points. A legend label identifies them as mean shift centers. The plot is labeled to show that mean shift finds dense regions without requiring a preset number of clusters. The axes identify the 2 features being compared, and the legend clarifies elements such as cluster centers. The visualization is then displayed for analysis. This script shows mean shift clustering on a synthetic dataset with 3 dense regions. It creates and scales the data, applies mean shift with a bandwidth of 1, and reports the Scikit-Learn version, bandwidth, and number of clusters found. The results are plotted with points colored by cluster and centers marked, illustrating how mean shift finds dense groups without requiring the number of clusters in advance. In this lecture, you learned to apply k-means and mini-batch k-means to unlabeled data, use inertia and silhouette analysis to compare cluster counts, and fit affinity propagation and mean shift with key parameter controls. In the next lecture, Lecture B, we will go over spectral hierarchical.
Thank you for your attention. See you all in the next lecture.